which was, I need some definitions. An ionic or electrostatic force comes from an ionic bond, and an ionic bond comes from a metal bound to a nonmetal. So I accept that as a working definition for both ionic bonds and ionic or electrostatic forces. Okay, so that one's good. I'm okay with that. But we have three more forces below. Well, we need to define those three more forces. Which of those forces do you have a definition for that you're like, yep, this is right? You got one?
The London dispersion and van der Waals, I just have like a temporary dipole to dipole combination that creates energy.
Okay. And a temporary dipole-dipole is absolutely a phenomenal definition for the London dispersion or van der Waals force. Okay. So let's look at the two structures that have been identified as London dispersion or van der Waals by your classmates. We have H bound to H the top, which we have three people confirming that one. And we also had a confirmation that C bonded to O was an example of London dispersion. Okay. By looking at H bound to H and carbon bond to oxygen, does anybody see dipole? Does anybody see temporary? Okay, so that definition is a bit useless. I'm not saying it's wrong. It's a beautiful definition. But if you can't look at the structure and say that is temporary or that is dipole, that definition isn't a working definition. That does not allow us to answer the question. We need to be able to look at a structure and draw that conclusion very quickly. So while I like that definition, we're going to have to erase that. We need a better definition. What do you got? What did you have, Emily? That? Okay, so I look at those and I say, oh, that's nonpolar covalent. What is nonpolar covalent? No difference in electronegativity. How many of you memorize the electronegativities? What is the electronegativity, Megan, of lead? Okay, so we haven't memorized the electronegativities. So while I like the idea of having similar differences in electronegativity, or very similar electronegativities, nobody's going to memorize the electronegativities. Okay, so we need something a little bit better than that. What do you have?
It's when one atom combines with another atom, or anything containing carbon and hydrogen, or carbon and hydrogen.
I will accept anything containing carbon and hydrogen.
Okay. And then, like...
Any bond between carbon and hydrogen is technically nonpolar covalent. But then the next part we're going to run into is you said any atom to any atom. Well,
same atom.
The same atom bonding to the same atom.
okay. How does that work for us? If the electronegativity on fluorine is the most electronegative element on the periodic table, when I bond it to anything, I should have a large difference in electronegativity, shouldn't I? What if I bond fluorine to fluorine? There's no difference, and now the bond I have, non-polar covalent, which fits under our London dispersion. Okay? So anytime we have the same atom bound to the same type of atom, that's going to classify as non-polar covalent. Okay? The other one we can work with is anything with carbon and hydrogen. So if we go through and apply those definitions to our structures, hydrogen bound to hydrogen is same atom to same atom, which means non-polar covalent, which means London dispersion force. So great. Those three people that all agreed that hydrogen bonded to hydrogen was London dispersion, I completely agree with you. What about carbon bonded to oxygen? Is that carbon and hydrogen? No. Is that the same atom bound to the same atom? Does carbon bonded to oxygen match our nonpolar covalent definition?
They're both nonpolar.
Okay? They're both nonmetals, so they are both covalent, but are they nonpolar covalent? No. Does carbon-bound oxygen classify under London dispersion?
No.
Not really, and we'll define that really in a little bit. Okay? As an interesting observation, I drew 4 structures and there are 4 forces. It's a 1-for-1 match. So if we agree that hydrogen bounded to hydrogen is London dispersion, the rest of them should not match London dispersion, roughly. Okay, because I said the strongest force. Okay, what else do we have to look at? We've got 2 more definitions. Dipole to dipole. When do I have dipole-dipole? Okay, I need from a polar covalent bond. Okay, so we're again using terms that we can't work with. I need a new definition for polar covalent. Come on, at least 17 of you watched the video. Non-metal to non-metal is the same thing as non-polar covalent. Sorry, Naya. So our polar covalent, if we think back to our Lewis structures, remember we had the paper? We said, okay, if we pull on these corners, if the paper moves, it's polar. That's polar covalent. Okay, so there's a structural effect to polar covalent. There's also an electronegativity effect. Okay, the electronegativity effect is that we have a difference in electronegativity that is not so great that it becomes ionic, and not so small that it becomes nonpolar covalent. Okay, well, when is that going to happen? We could quantify it, as Obed miraculously memorized those. I guess I did it, so it couldn't have been that hard. Memorize the numbers to those electronegativities, but then we'd have to know the electronegativity for every single element. Okay. 18 people. What was that definition? Officially everybody, because we talked about these definitions earlier in the semester. Whoops, I can't spell. Everything that isn't nonpolar covalent and everything that isn't ionic. That's our polar covalent bond. So when we go through and now look at the remaining structures, okay, we classified sodium chloride, our middle one. We classified for sure our hydrogen, our HH. Okay. Everything else. Okay. Well, HH was nonpolar covalent, so I can't possibly get a dipole out of HH. Sodium chloride was ionic. Can't possibly get a dipole out of the ionic. Okay. I look at water. Okay. The OH bond, is that nonpolar covalent? No, so it's not nonpolar covalent. Is it ionic? No, so it's not ionic. What does that make the OH bond? Polar covalent, which then means dipole-dipole. I get a dipole-dipole force out of that. Okay? So I agree, okay, with one person. Okay? Is there another compound that could have matched that?
The CO?
The carbon-oxygen single bond, or triple bond, CO. That also matches that definition. We don't have same to same, we don't have carbon to hydrogen, and there's no metal. It's not ionic, it's not nonpolar covalent. It then, by definition, is going to be polar covalent, which means dipole-dipole. This should already start to cause a bit of an issue. We had 4 structures, and I said of those 4 structures, each of them matched. It's not looking so good for that definition. Okay? So what is left? Okay, number 1, actually looking at all our arrows, we got that connected. Really the only force left is hydrogen bonding. How do we define our hydrogen bonding?
As a hydrogen.
Okay. First condition, it should have a hydrogen. Hence it's called hydrogen bonding, right? Okay. What else? bound to an element with very high electronegativity. What are the three most electronegative elements? Fluorine, nitrogen, oxygen. Guess which three elements generate hydrogen bonding forces? Fluorine, oxygen, nitrogen. We must have a hydrogen bound to one of those three elements. If we have that, then we have the potential for hydrogen bonding. Okay? So if our two compounds that have not been circled, we have carbon bonded to oxygen. Does that satisfy our hydrogen bonding rule? Carbon bonded to oxygen? No, we have to have a hydrogen bound to oxygen, and I have a carbon. So carbon monoxide does not have hydrogen bonding. Okay? So good, we didn't connect that. How about water?
Yes.
Do I have a hydrogen bound to oxygen? Yes. That connection is true. What about hydrogen bound to hydrogen? That connection is false. I need to have the hydrogen bound to oxygen, nitrogen, or fluorine. Hydrogen bound to hydrogen is not fluorine, oxygen, or nitrogen. Okay? So H bound to H is London dispersion. Sodium bound to chloride is ionic. H2O is hydrogen bonding and dipole-dipole. But didn't I say it was only a 1-for-1 match? I did. And I also said I only wanted the strongest force. H bonded to oxygen does generate a dipole-dipole force. It also generates a hydrogen bonding force. Which one is stronger? Hydrogen bonding. Which means for the sake of this assignment, I should erase the dipole-dipole going to the water because I asked for the strongest force per each of those compounds. Make sense? So to answer these types of questions, you have to be able to recognize the types of bonds and then translate that to the definition for those forces. Once you have the force, you then know something about the strength, where ionic is the strongest and London dispersion is the weakest force. Watch the video for an explanation on why. Okay? What's that?
I was talking to myself. I'm going to have to rewatch it.
It's okay. That in and of itself is actually pretty boring. What we actually want to do with this is use it. Okay? So to use it, where's my buttons? What is going on here? Whoa, oh, that's why. So to use it, what can we do with these forces? Phase transitions are dictated based off of forces. Vapor pressure, off of forces. Viscosity, off of forces. All of these physical properties that we could monitor and look at are all based off of the intermolecular force. How do we determine the intermolecular force? We look at the bonds. That's what this chart is trying to set up. We've got bonds and forces set up in a spectrum. Ultimately, it's just the interaction between any two atoms. And what we decided is that at some point that interaction is so strong that it is no longer classified as an interaction. It is classified as a bond. And if it's not that strong, we classify it as a force. Okay? Both of them are types of interactions. Both of them are just looking at how strongly they interact. If it is a weaker interaction, we call it a force. A stronger interaction, we call it a bond. The bonding interaction is actually so strong that we transfer electrons. The force does not transfer electrons. We just kind of see, hey, yeah, I see some electrons there. That looks kind of cool. I'm going to go closer to it. But that's it. If that force gets strong enough, what can happen? Then we can change the bonds. Okay? Or they get married. So, whoops. I had you go through and predict your melting points and boiling points by looking at the last compound. Okay? I remember what that blank slide was for. It's looking at our phase transitions. Okay? I want heat versus temperature. I'm going to put heat on the x-axis and temperature on the y. If I start with ice, where would I start? Where would ice be on this chart?
32 degrees.
Too specific, but we could get colder than that.
0.
Where? Oh, vertex. That's mathematics for there. Okay. Very low heat, very low temperature. Okay, that's where our ice would be. What happens as we start to add heat to our ice?
Melts.
Not yet.
It increases, the temperature stays at 0.
Still not even that yet. If I have ice, what temperature do I have ice?
32 degrees.
32 degrees. Has anybody been in Flagstaff where it has been colder than 32 degrees? Okay, wow, that's kind of cool. You were at a place where it was colder than 32 degrees. And because it was colder than 32 degrees and ice only exists at 32, there was no ice, right? No, you saw ice still? But you said ice only exists at 32 degrees. 32 and under. If I'm at a condition of an extremely low temperature and extremely low heat, I am probably like negative, let's push it to the extreme, 273 Celsius. Okay. Absolute zero. What happens as I add heat? The heat goes into our solid. What happens to ice? It goes up in temperature to now, or does it go up in temperature? Does our ice change temperatures if we're at negative 273 and I add heat?
Slowly it does.
Slowly it does, which means the temperature does increase. Until what point?
It melts.
Until I achieve my boiling point, or sorry, my freezing point, or my melting point. Now we're at our 32 degrees Fahrenheit or 0 degrees Celsius. Okay. What happens now when I add heat?
It continues to rise, but very slowly.
Does it continue to rise? So when it's at 32 degrees in Flagstaff, do you still see ice?
Are you adding heat still?
We're still adding heat. There's still heat in the air, yeah.
Yeah. Keep going.
The temperature actually does not increase. I know that's what you said, but you said it too early. What happens to the temperature?
It stays the same until
It stays the same until what happens?
So more heat is applied.
Nope.
it changes state.
When it changes state. At this bottom part, I am currently a solid. Okay. As I continue to add heat, what eventually happens? That solid becomes
Liquid.
a liquid, but there's still solid there. How do I get the rest of that solid to become a liquid?
Keep heating.
I keep adding heat. But since there's still solid present, what's the temperature?
The same.
It's the same. Which means I see a flat line. That's supposed to be flat. When does that line stop being flat?
It's all liquid.
As soon as all of my solid has moved into a liquid. Okay. Now what happens when I continue to add heat?
It goes up again.
It goes up again. Until what point?
It boils.
It boils and turns into a gas. What happens? At 100 degrees Celsius, all of my liquid instantly becomes a gas?
No.
No. It's a gradual transition. I see again a flat line before it peaks again, or before it rises. And I have my gas, I have my liquid, and then I can have my melting point and my boiling point. Okay. What dictates the values of the melting point and the boiling point?
Density and
It's nothing to do with density directly. What phase do I have here?
solid.
Okay. How do I know it's a solid?
Close together.
They're all close together. Why are they close together?
Bonded.
Bond is a bad word in this case. They are attracted through a force. If it was water, that force would be hydrogen bonding. When I look at going from the solid to the liquid, what happens? What am I breaking? If I break the bond, what I end up with is something like this. Or in the case of water, that's not supposed to look like a pumpkin. Is that what happens? When I boil water, I get hydrogen and oxygen? No, what happens? What happens to the chemical identity of the water? It stays the same. Do I end up breaking the bond? Oops. Still have circles. How do I know that's now a liquid? More space. What changed as I went from the solid to the liquid? The strength of the attraction. Which attraction? The intermolecular force. When we're looking at our melting points and our boiling points, it's all based off of the force, not the bond, which is a very common misconception. Everybody goes, oh, well, that's a really strong bond, so it's going to have a really low boiling point or melting point. It's actually the other way around. Okay? What is breaking when we go through our phase transitions is the intermolecular forces. Okay? It's what's keeping those compounds interacting with each other. Okay? So how does that help us when we get back to looking at a structure? When we look at the last one between A and B, okay, it's officially an alcohol and a salt. To determine the melting point or boiling point, I need to look at the force. Well, what is the strongest force in the A structure? Well, maybe it's helpful to identify all of the forces. Once we have all of the forces, we can then identify the strongest of them. What bonds do you see in that first structure? I don't accept hydrogen.
No.
Yeah. I said bond, didn't I? I could be. I did say bond, didn't I? What bonds did you see? Yeah. So there's an OH. There's a CH. There's a CC. CO. Okay. This comes from drawing out a Lewis structure for this one right here. We take a look, we'd start with our carbon. Remember Lewis structures? What did the formula mean? What bonds are present in there? Well, we saw an OH, an oxygen bound to a hydrogen. There's a bond. There's an oxygen bound to a carbon. There's a bond. There's a carbon bound to a hydrogen, and there's a carbon bound to a carbon. Are there other carbon bound to hydrogens? Is that a carbon to hydrogen bond? Yes. Do I care? No, because I've already identified it. We only need to identify it once. That's it. Because if I look at a carbon-hydrogen bond, what type of bond is that? Close? Officially, and according to my definitions, yes. What type of bond is carbon to hydrogen? This is why you wrote down all those definitions earlier. A nonpolar covalent. Well, let's look at another carbon to hydrogen bond. What type of bond is that? Nonpolar covalent. Well, how about a different carbon to hydrogen bond? Nonpolar covalent. What if I draw the carbon to hydrogen bond really, really big? What is it now? Nonpolar covalent. If I have a carbon-hydrogen bond, what kind of bond is it? Nonpolar covalent. I only care about one. Once I've identified that one, I'm fine. What type of force, as I choke on my own spit, what type of force is in a carbon to hydrogen bond? London dispersion forces, or LDF. What type of bond or force is between a carbon to carbon bond? London dispersion force. What type of force is there between a carbon to oxygen bond? A dipole-dipole. What type of force, that says dipole, is there between an oxygen and a hydrogen? Which of those forces is the strongest? Hydrogen bonding. So now when I'm looking at structure 4A, I only need to identify the strongest force, which is hydrogen bonding. How about 4b? What is the strongest force in 4b? Well, I see a carbon bound to a hydrogen. What type of bond is that? Nonpolar covalent, which gets us London dispersion. Carbon bound to carbon. London dispersion force. Carbon bound to oxygen. Dipole-dipole. Well, that's a stronger force, so I'll focus on the dipole-dipole. But what else is left? Oxygen to sodium. What type of bond is that? Ionic. What type of force is that? Or electrostatic. Of all of those forces, which one was the strongest? Electrostatic, dipole-dipole, or London dispersion? Electrostatic. Now we can compare 4A to 4B. Which one has the stronger force? B, which means stronger force means each of those molecules are holding tighter to each other, which means is it going to require more energy or less energy to rip them away from each other? More energy. How do we measure that energy? Temperature. Which means to get 4B to melt, I have to supply more heat, which means a higher temperature value, which means higher melting point. 4B is our answer. Right. How about 1? I was like pulling teeth, so I'm going to make you do 1, because it's even worse. I heard 1B and I heard 1A.
Okay.
Who says A? Who says B?
I say B, and here's why.
Okay, B wins. Let's go with your explanation.
Because they both have the same type of bonds, and then B has more. So if A has different types of bonds, that would have resulted in it being stronger, even though there was less. So we could have done A, but since they were both, B was bigger. So we had to go.
So first we would look at the strength. And the strength between them is the same. They both have London dispersion forces as their strongest force. So that is not a deciding factor between these. So we now have to do further steps or further evaluation between them. Okay? If we take a look at these two pieces of paper, okay, and I put them together, okay, what keeps them together? And don't tell me my hand. Nothing keeps them together? So I put them there, and they're just going to...
Force of gravity.
Force of gravity keeps them down. That doesn't keep them on top of each other. Could have just easily slid laterally.
What about the force of oxygen?
The force of the table keeps it up. That does not have nothing to do with the side force. What's that? Nothing? Say that again, Sebastian. There is an attraction between these two pages. Okay? There's a friction there. That attraction keeps them together when we set them down. If we compare that attraction to... All right. And burn more trees. The attraction between these two sheets of paper. Do they have different strength forces? No. It's just both raw friction. Okay. Are they going to require the same amount of energy to separate? Why not? It is smaller, which means there is less contact between the two pieces of paper, which means there's less interactions to break. With the two full sheets of paper, what has to happen? I have to break every single point, contact to slide, which apparently I can't do. Okay. Each of those points must break. That requires more force. What's happening when we look at 1A and 1B? The same thing. In 1A, I have a smaller molecule, so those molecules stack on top of each other, and they only have that point of contact. What happens with 1B? It's larger, which then means more contact points. So the force is the same. They're both London dispersion forces, but 1B has more London dispersion forces. So it can counteract the smaller molecule 1A. just to be annoying, because we're out of time and I'm going to do it anyway. Which has the higher melting point? 1B or 4B?
4B.